It's December 19th. Have been doing some more algebra for about an hour and a half or so. It's a pretty good session. Yesterday, I was really stumped on congruences over the set of, they define over the set of all integers, positive and negative. But congruence is just modulus from computer science, or I like to think of it as just the remainder after you divide something. So you divide one number by another number, you get a remainder, and the remainder is the number that comes out, which is what the congruence is about. So apparently there's somebody defined the remainders that you get after dividing by a certain. You pick a single number to do the mod operation with. So it's basically a mapping. The mod is a mapping. So the remainders, you only get a finite number of them, and they repeat. So you end up with a finite set. You map to a finite set, and each integer, they just call them a residue class. So if you take 3 mod 2, that's 3 divided by 2, and then 1 is the remainder, so 1 is a residue class of 3 mod 2. So it's just really confusing for something simple. And then the residue class is because it's a finite set of integers. Turns out that it's got its own rules of addition, multiplication, and then a couple other things. There's one law with a constant. There's a law with a residue class multiplied by some constant is congruent to 1, I think. If the residue class is prime, there's some stuff going on with prime numbers and residue classes. So prime numbers pop out to be important again. And the thing that was confusing me last night, I understand now. So basically, residue class is a single number. It's not actually a class of objects, it's just one thing. So with the residue class, if you have a residue class defined by, you can get back a particular residue class if you multiply, or you can get back a set of residue classes, the entire set of residue classes, by multiplying all integers by one residue class. So you do the mod operation, you get a finite list of numbers. You pick one of those, which is not non-zero. You can't pick 0. You pick one of those numbers, that's called the residue class. You multiply it by all the integers, negative infinity to positive infinity. And then you take the mod operation of that product of the original mod, which defined the original residue classes. The residue class is set. And then you get back that you can get back the residue class if the residue class set, if the residue class that you pick to multiply by all the integers again is co-prime with the mod value. So apparently it doesn't work out if those are not co-prime. So I haven't checked that out yet, but I know that it works if you pick them co-prime. So it's pretty confusing, but it's mostly the terminology. The concept is really easy. And then there's this little equation that I don't really understand where they've so you basically you have an identity mapping with the coprime residue class, because you just recapitulate the original residue classes set. So those are equivalent. So you get out the same integers, and then I guess you can go a step farther and say that if you multiply all the numbers in the set, you end up with the same product, because you have all the same integers in both sets, which makes sense. But you have to remember that it's all modulus, whatever number you picked. But somehow you can pull out the common factor residue class that you multiplied by in order to get that copycat set. You can pull it out of the product and sort of out of the modulus. So I'm not sure how that works, but it does. And then you end up with, so that residue class that you multiply every integer on the z in the z set, which is negative and positive integers. That residue class inside a product if you multiply all the objects within the set, you're multiplying that residue class over and over and over again. So you can pull it out and collapse it all, write them all next to each other instead of in separate. Write them separate, so you end up with that integer times itself, times itself, times itself, times itself, and then you take the mod of that, and that turns out to be 1, which is called Fermat's theorem. So I'm not really sure why that's important, but it's pretty cool. And that's where I stopped for today. So it's a good day, good math day. About it was probably hour 10, hour 20 minutes, but time went pretty fast. So that's good. So see you later.